Hello everyone, my name is Rachel Seevers and I'm a senior from Paul Laurence Dunbar High School in Lexington, Kentucky. And in this research, I created a novel aircraft wing design that can improve the efficiency of a standard military aircraft by up to 26.6% just by using high-speed air. You see, I am the inventor of the virtual winglet, and the way it works is actually quite simple. The high-speed air ejected at the underside of the leading edge of the wingtip is also a low-pressure system, which attracts the surrounding higher-pressure air down with it. And this can help prevent the full formation of wingtip vortices and prevent flow separation, which are two of the most detrimental parts of flying an airplane, and a singular device that can be used on all aircraft. So in this experimentation, I focused a lot on military aircraft, or STAL aircraft, which stands for Short Takeoff and Landing. I specifically focused on these because many of these types of airplanes need to be able to be extremely maneuverable and efficient to have the upper hand in things like dogfighting or long-range missions. But beyond the improvements in range or maneuverability or fuel efficiency, there's one major aspect of military aircraft that really attracted me to pursue that area of study. And that's the fact that there's a pilot in every single one of these aircraft that are sacrificing their lives for ours. And if there's anything I can do to help save that life, or make flying safer, or less worrisome for that pilot, then that is the greatest gift I will be able to give them. But the benefits of the virtual winglet are not just things that can be experienced by pilots or by the men and women who sacrifice their lives on a daily basis. In fact, the benefits of the virtual winglet are not exclusive to men and women at all. In fact, one of the greatest beneficiaries of this device is the environment itself. By improving the lift-to-drag ratio of these aircraft by up to 26.6%, I am also thereby decreasing the amount of carbon dioxide emissions every single year by up to 112 million tons. So I tested this device using a 4-part experimental design that included 2 parts physical verification and 2 parts computational fluid dynamics, or CFD modeling, which took place on a computer. And it was this unique experimental design that allowed me to really get my hands dirty with engineering, not only making the device itself, but also inventing and making some other pretty cool things.
Like a wind tunnel!
But also a flow tank, which is basically a wind tunnel, but uses water instead of air, which allowed me to dye certain areas of experimental flow using food coloring and be able to collect really great qualitative data. I also collected quantitative data using my CFD analysis, which gave me over 1,000 data points per second of flow. And I was able to collect all of these data and all of my runs on my own personal computer. But the problem was that I was stuck. I had no idea how to use computational fluid dynamics, and I didn't even know where to start. But I decided not to give up and look around my community to see if anyone was available to help me. I started by looking at Toyota because many simulation models started out as car crash simulators, and I thought there might be somebody familiar with that work there. But what I found was a mentor at Lexmark who was used to using simulation modeling to test the movement of paper through a printer. So I reached out to him and asked him if he could teach me how to use CFD modeling. And he was super interested in my work and really helped me take that next step towards collecting quantitative data and making my project a viable option for flights everywhere. And these are flights that include the ones being done by my model aircraft that are testing the virtual winglet in a physical environment. The virtual winglet is no longer just a theoretical proposition or an idea I'm working on in my mad scientist lab down in my basement. It's a real device that's being tested on real prototypes in a physical world and can be implemented on real aircraft. So all of this started a couple years ago when I was on an airplane blessed with the window seat and I looked outside, and there were giant white bands of fluid moving over the wings, and I was terrified. I thought we were going to die. I was sure that this was the end, because those white bands, they must have been an engine failing or the magic dust keeping the aircraft afloat evaporating into thin air. I was reminded that that wasn't magic dust. That was just the air going over the wings and being condensated because of the pressure gradient. And that one moment made me realize that I had no idea how airplanes flew, just like I think a lot of kids don't. But instead of being scared by the unknown, I was fascinated by it. So when I got home from that trip, I locked myself in my basement for 2 weeks, and before I knew it, I had built my own wind tunnel to study airplanes from the comfort of my own home. I was able to face my fears head on and use knowledge as an antidote for my fear. But even beyond fear, even the things that we aren't afraid of, there's always something else out there that is unknown to us that we can figure out. And that knowledge and that curiosity is what drives scientific research today. And that's why I take such a passion and such an interest in continuing that curiosity in students of all ages. I've launched my own outreach program called STEM Femmes, a derivative of an organization I had previously made called Dunbar Girls in STEM, that has high school females go to underprivileged elementary schools in my community and work on hands-on experiments with kids that may not usually have those experiences available to them. And in one of these lessons, I was able to teach the kids how airplanes flew, in a lesson that taught them things way before I even knew how airplanes could fly. And I saw such wonder and excitement on their faces that made me realize that there is always something else out there that we can do to help our community. And it doesn't have to be making a new airplane wing, even though that can have such a positive impact. It can be as small as passing on the baton and teaching somebody else something that you know. That's a passion that I have in my own work. And that's what makes my research special. It means the world to me, but it can also mean the world to a person that it helps save, or a pilot whose life it makes better simply by existing, simply by ejecting high-speed air in a certain place on the wing. I, a high school student, can change the way we fly today.